Okay. What planet is that?
Mercury.
What?
Mercury.
No, it's Earth. Okay. I was like, oh no, awkward. Okay. Yeah. So you are right about there. You know. So yeah, that's Earth. Okay, and we do a lot of comparisons to Earth. We think we're all about that, but honestly, and we are kind of. But the other thing is, it's what we know. So. Starting out with Earth actually kind of has this structure internally. And the way you're like, how do they know that Earth has kind of this silver? No, it's not silver. How do we know that we have a core and actually there's a solid part to the core and a liquid part to the core? And how do we know that that there's this mantle? And the answer is, if you've ever seen Tremors, okay. Yeah, it is so cool. And Tremors starts out basically, I don't know about the sequel, but they're out there in the desert and they have these probes stuck in the ground and they're looking for seismic activity. Okay, they're kind of looking for, basically, if you were to tap this, and they use this in the movie, if you were to tap this over here, and you're over here and you feel the waves coming through the ground, you can understand what the nature of that ground is, okay, because of the waves. Okay, so that's kind of how we got to understand what the interior of the Earth is like. So when we talk about these terrestrial planets, the four inner planets, so Mercury, Venus, Earth, and Mars, they all kind of have the similar, okay? So we're going to kind of compare. So kind of from left to right, you see size-wise, okay? This isn't in the order from the sun, right? But Earth is the biggest. But Venus is a close second, okay? Mars is a fair bit smaller than Earth, and that has its consequences. Okay, then we have Mercury is smaller, and Moon is the smallest. Of course, the Moon isn't a planet, okay, but kind of showing it relative size. One thing that might kind of strike you is the size of that silver thing. Remember, that's the core. And the core that has similar composition for all of these planets in the Moon. The core is like the metals, okay, iron and such. Okay, but you can kind of see they have different proportions of the different components. So the kind of the tan there is, we'll talk more about this, but the tan there is the crust. You've all heard of crust. I mean, some of the stuff we're going to talk about, you're like, I've heard of that before, and you're right. Okay, so crust. Okay, and then this color right here is the mantle, orange. Okay, and then I said that this is the core inside. How many people have seen the movie The Core? Yeah, it's good too. It's kind of silly, but it's good. Okay, so one other thing you may or may not have experienced before, and we'll talk more about it, is this thing called a lithosphere. And the lithosphere is the crunchy crust and the liquid part of the mantle. Okay, so yeah. So I love the term planetary, and I know it's kind of chopped off up there. Planetary differentiation. And if you remember, or if you've ever used like oil and vinegar salad dressing, okay, Italian salad dressing, then you have an idea of planetary differentiation. Because what happens when you take that and set it down is, let's see, the water's more dense and the oil floats. Okay, they separate because they don't like, their polarities are kind of different. Okay, so kind of like that, dense stuff over time with all of these terrestrial planets, dense stuff has fallen to the center. Because, well, let's see, how do I describe this? When we talked about the formation of the planets, we said it's kind of like a snowball sort of thing, right? Kind of like, we called it accretion, more things getting bigger and bigger. The other thing is, as things got kind of bigger and bigger, and this object was, planetesimals were kind of combining to make one big thing that's ultimately going to be the planet, there was heat involved, okay? And so kind of the thing was kind of ooey gooey, okay? So it got chunks and it got ooey gooey. And that's important for planetary differentiation. Because, for instance, if your Italian salad dressing, if it was like chunky solid, is it going to separate into its, no, it's got to be ooey gooey. Okay, so planetary differentiation occurred then. So the heavy stuff sank, the dense stuff sank, and the light stuff rose. Okay. So lithosphere, like I said, it's kind of two layers. Lithosphere, it is the, like this said, it's the crust, okay, the rigid crust, okay, and let's see. No, I guess I'm going to change. I said this was liquid actually. This is mantle because it's red. This whole thing is mantle, okay? But this actually is rigid. This is the rigid crust. This is the rigid mantle. One of the things, and I'll go ahead and draw it on here, that probably the core would tell you, the movie The Core, is as you go from the outside of the Earth towards the center, there are no dinosaurs. But the other thing is it gets hotter, okay? And so honestly, that's why the mantle here, which is all orange, the top part of the mantle actually is solid. I'll put an S for solid. And this part right here is, I need to change my color. The inner part is liquid. This is a liquid. Okay. So the lithosphere is the solid crust and the solid part of the mantle. Because here in a minute we're going to talk about something called plate tectonics. You're like, tectonics, plate tectonics. You probably ran into that in earth science before. The fact that the Earth's crust is basically broken up into slabs and they kind of slide around a little bit. Okay, it's tectonics. So that's where the lithosphere comes in, kind of slides around. So, is she not adorable? So, kind of like silly putty. If you're gentle with silly putty, you can go, oh, nice and gentle. But if you're not gentle with silly putty, doesn't she look disappointed? So there actually is, rocks can be stretched and kind of remolded, okay? But if you were to take a rock and you were like, I want to right now deform that rock, and you took a hammer, okay, that would be like the bottom part with the whole silly putty. So rocks over time can and have been deformed, but okay, which is kind of fun to think about. So you see those kind of lava lamp looking things? Okay, those are representing movement in the liquid part of the mantle. And it really reminds me kind of a lava lamp. Okay. This is hot in here. Hot, hot, hot. So what that does is it heats up the bottom part of the liquid mantle. Okay, right here, this is hot, and this is hot. Okay, and one of the things, just like hot air, hot mantle will rise because hot mantle has expanded and it's ready to rise up away from the core. So what we have there is then basically this sort of leg, okay, where I've kind of drawn in hot rising, hot rising. So this sort of red is trying to show you cooling. I'll change it to a different color. Okay, up here, this is cooling down. Okay, and then what it does is it kind of completes a cell, cooling, and it goes back down. So that's what's happening under the lithosphere, okay, in the liquid mantle. And I mentioned a lava lamp because if you've watched a lava lamp, basically you turn on the light element, and what do you see? You see movement. Okay, and what's happening is that liquid that's closest to the heating element or the light, it heats up and expands, and now it's less dense than its surroundings, and it will rise. It will cool off, then it will sink. Convection cells. Okay. So, if you've taken meteorology with me, or maybe you didn't have to take meteorology, but heat can be transferred this way. Basically, energy goes from the core outwards via convection. Heat can also be transferred via conduction and radiation, and they're both shown on here too. In conduction, I emphasize that conduction is from molecule to molecule. Let's see, oops, go back. Okay, so conduction, molecule to molecule. molecule to molecule. Okay, no blobs of moving material. So the conduction is just right here within the lithosphere. Okay, so this is conduction. It's like wiggling its way, or not wiggling, but moving its way out. If you're boiling water on a stove and it's been there for a while and you go to grab the handle of the pot that you're boiling the water into, it's hot. Okay, or you're boiling the water in. The handle is hot because of conduction. Then radiation, we've talked a lot about electromagnetic radiation, and here it's I'm free. Okay, those little photons of energy are free. That's called radiation. Okay, so that's kind of how that works. So does it seem like the Earth might be cooling down? You kind of buy that? Because we have a hot center ever since kind of it was ooey gooey, okay, planetary differentiation, okay, and it basically kind of moves energy, heat up via conduction, okay, sorry, up via convection, and then conduction, and then radiation. So it's kind of an overall cooling sort of thing. We are cooling. Okay. So let's go ahead and look at the same figure we looked at before, just to remind you kind of the relative sizes. So what's the next one? Oh, you already have it. Venus. Okay. Notice proportional-wise, they're kind of similar, aren't they, with regard to the core and the mantle and the crust. Okay. Mars, a little bit smaller. Mercury's got a heck of a core, doesn't it? Okay, it really does. So the size here, arranged this way, hopefully kind of points out size. The deal is the smaller the world, the smaller the planet, you can kind of point, starting especially with Mars, the faster it's going to cool off. The Earth's cooling off, and Mars cooled off even faster than that. It's kind of intuitive, like if you have pizza, okay, and you make like a big old family-sized pizza, Papa Murphy's, okay, that thing's going to stay warm a while, but if you take one piece out and you set it over here, okay, this one's going to cool down and this is going to stay warm for a while. True situation. Okay. So keep that in mind. So when we talk about volcanoes and earthquakes, which I don't know, some people might get sided with. Volcanoes and earthquakes, that's when a planet is alive. Does the Earth still have volcanoes and earthquakes? Yeah. And to be alive, it needs to have a little bit of fluid here in the mantle region. The thing about, I'm going to put dead in front of Mars too, the thing about these three small objects is they've been around long enough that, oh, Mars, I guess I have a question mark. They've been around long enough, they've cooled down, they no longer have any sort of liquid here. Mars is geologically active, us, and Venus. Okay. So, here's the deal, or a deal. If you take like a magnet, where you're looking at in the black thing there is like just a bar magnet. It has a north magnetic pole and a south magnetic pole. And you can't see it, but there are what we call magnetic lines of flux. And I think they come from the north and go into the south. Not necessarily directional, but you can kind of see they go out like that. They're invisible. Okay. This reminds me of, have you ever played with like those little things where you make give the man a beard and an eyebrows? That's what this reminds me of. Okay. Doesn't it? Yeah. Okay, so you can't see those lines of flux. Okay. So we can create a magnetic field without a magnet. And here's how you do it. Basically, you get charges moving around. And kind of that's what's being shown here. That's supposed to be a battery, your Duracell battery, copper top, okay? And one of the things batteries are great at is if you connect a wire to both ends, you can get electricity, or you can get electrons chasing each other in a circle. That's what's being done there. The other thing is to take some sort of inert object, and this is probably a metal, I guess, okay, and wrap that coil that's going to carry those electrons. Okay, sorry, coil that wire around that post. Okay, so now you have electrons coming from the battery, going around, and going back in the battery. So here's my deal. If you can get electrons doing this in a circle, okay, can you see the pink magnetic field? Okay, that's just like a magnet. So we have created a pink magnetic field, okay, by having electrons go in a circle. Well, you're like, what does that have to do with astronomy? Okay. Scale that up to planets. So that gray thing, okay, we've been calling that gray thing that all terrestrial planets have, the core. So now we're taking a closer look at the core. So within the core, actually there's, and if you watch the movie The Core, I think they talk about this, because it's like it stops rotating. Really, the core is spinning. There's two parts to the core. There's the solid part, inner part, and then there's it's almost like amniotic fluid. There's like the liquidy part, okay, of the core. So basically then, and I'll try to kind of maybe take my marker and show you what I'm trying to say, the inner part of our core, because I said we're geologically active, this part right here, okay, is liquid. Okay, and because it's liquid, it has similar to basically having kind of free electrons. They're free. Is the Earth spinning on its axis? Okay, it takes like 24 hours. It does one of these, 24 hours, okay? And then kind of related to that basically is also then moving those electrons. So now we're kind of like we're back to this middle picture where basically we have electrons moving. What does that create? An invisible pink field. I don't know if it's pink or not. Okay, but magnetic field. Okay. So magnetic field. Planets that have any sort of liquid in them, got it. Planets that are geologically dead, don't got it. Okay. All right. So why do we care about the Earth's magnetic field? The Earth's magnetic field creates collectively what's called the magnetosphere. Almost sounds like a cartoon character, like a, yeah. Okay, magnetosphere. So basically that's just kind of collectively what our pink is. Okay, magnetic field created because we have liquid in our core and we're rotating. Okay, so the magnetosphere actually then, we can kind of, it's not pink anymore, but on this it's kind of being shown as kind of a light blue. It's actually a protective cover, okay? You see over here the sun, and we talked about when the sun turned on, basically it began, remember this idea of solar wind? Yeah. Well, solar wind's cool, and it basically goes in all directions, including towards the planets, but it also carries charged particles, and it can really, you know, be difficult on a planet. So what happens when solar wind from the sun coming towards the Earth hits us is basically, can you see some of this deflection? Okay, solar wind, harmful radiation, is deflected by our magnetosphere. Cool? Well, it's not all deflected, so you kind of see some kind of sneaking in. Okay, this region, this kind of pink region, you're looking at kind of a slice of the Earth and our magnetosphere. This pink region right here are called Van Allen belts, actually. This is charged particle belts, but usually called Van Allen belts, named after the scientist who found them. The thing about Van Allen belts is they are kind of where some of the particles that get through, they're where they go. Okay, some of the particles that get through the outer edge of our magnetosphere kind of find their way to what we call the radiation belt, the Van Allen belts. So here's the deal then. See if I can kind of explain this. And the slide already says, it's this phenomenon that we've set up, charged particles coming from the sun, that give us our northern lights. But here's the catch. This is ongoing, and we're going to talk about sometimes the sun is more rambunctious than others. So when the sun is really rowdy, basically it sends us too much stuff that can be accommodated or deflected and even kind of stored here. And when we get too much, like coronal mass ejections or solar flares or coming our way, basically stuff is going to fall through, and it's going to fall through our weakest area, which is the poles. And when it falls through the poles, the particles are going to cascade through Earth's atmosphere then, because they made it, because they're on overload, and they're going to create these pretty northern lights. Have you ever heard the whole, when the poles flip, oh my gosh, what are we going to do when the poles flip? And what they're talking about, they're not talking about the Earth's rotation poles. They're talking about our magnetic poles. And there actually is some credence to this. Not to scare your kids or anything. But before our sun blows up, this is probably going to happen. Okay, so you kind of got a sense, hopefully, for how protective this is. What we know has happened in the past, and I don't think they really know why, but basically our magnetic North Pole and our magnetic South Pole has flipped. And literally, in order to flip, they don't just do it like a genie. They literally have to go like this. Okay, well, if you do that and kind of keep the same orientation as I've got up there, can you see where we're mid-flip? That's a bad thing. Because basically we've got our vulnerable spot. Now this isn't the rotation, this is the magnetic pole. Okay, vulnerable spot towards the sun. And then finish that flip. I think I've read it's like, and you can tell this in rocks, because it was like frozen, the different poles were frozen to represent in rocks. I'm thinking it's like 20,000 years or something.
Is solar wind an actual force that pushes things in space?
Yes, solar wind.
If a spaceship had sails like a boat, could it sail on solar wind?
Yes. And he's asking about solar wind and using it as a sail. Yeah, and actually, I think they're looking at maybe that technology to power our spaceship. So, spaceships, yeah. I agree. Uh-oh, reconnecting. Oh, very good. Okay. So I mentioned one of the things I'm hoping is that not necessarily in your dreams or anything, but you'll kind of picture something. When you think of Mercury, Venus, Earth, and Mars, kind of picture something. And next time, or either Friday or Monday, we'll talk about the gaseous planets. But this might be what you picture. Okay, Mercury, Venus, Tyree, Earth, okay, Earth, Moon, and Mars. And we'll talk a little more about that. It's not a happy camper. Okay. So, now this isn't just the moon, and this isn't just Mercury. All of the planets have been smacked around. One of the things that we talked about in the last chapter was the formation of our solar system. And remember we said that before things kind of settled down to the sun and the nice little calm planets orbiting the sun, there was definitely a time when there was all sorts of miscellaneous stuff that was not a planet yet. Okay, miscellaneous, what I call kind of crumblies. There were like miscellaneous rocks, miscellaneous icy rocks, or basically comets. Okay,